Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titrations. Let's get moving. Bam! So today we're talking about buffers and their preparation. So a buffer is a special case of the common ion effect and are composed of weak conjugate pairs. So I want you to make sure that you review the previous video, which is a weak base calculation number 3. We actually did a common ion effect or a buffer problem right there mathematically. Thus, strong acids and strong bases cannot make a buffer. That's critical. Okay? Buffers resist changes in pH by neutralizing or consuming or snarfing up either the acid or the base to maintain the pH of the buffer solution with a certain set of parameters. Some examples are of the following. Ammonia and ammonium ion. That's a perfect example. These are weak conjugate pairs. The acetate ion and acetic acid. Those are weak conjugate pairs. That's a perfect example as well. Sodium hydroxide and the hydroxide ion. Does that work? That sodium hydroxide is a strong base, and that is an absolute no. That does not work. Okay? How about hydrochloric acid and the chloride ion? These are also conjugate pairs, just as we had sodium hydroxide and hydroxide ion. Unfortunately, hydrochloric acid is a strong acid, and you cannot make a buffer with anything, either a strong acid or a strong base. So we're going to cross that one out as well. Here's another possibility of weak conjugate pairs. That is dihydrogen phosphate and hydrogen phosphate ions. That is also an excellent example of weak conjugate pairs that will form a buffer. Those are common ions. Okay, so we're going to take the acetate ion plus water gives me acetic acid and the hydroxide ion. Notice that this equation is balanced for both charge and mass on both sides. Okay, the Kb for this is 5.6 times 10 to the negative 10. Okay, the reverse of the reaction above of the weak acid with the addition of hydroxide ions has a K reverse. That is it, which is extremely large. Therefore, acetic acid can completely consume or snarf up, if you will, the hydroxide ions. I want you to remember way back into the equilibrium unit when we reversed the reactants and products of an equilibrium reaction, we took 1 over the K. So that's what we're going to do here is the acetic acid will consume hydroxide ions because the K reverse, that is 1 over the Kb, is so large at 1.8 times 10 to the 9 positive. Okay, so acetic acid plus water gives the acetate ion and hydronium ion. The Ka for this is 1.8 times 10 to the negative 5. We've actually used this equation on a couple of problems already before. The reverse of the above reaction of a weak base is the addition of hydrogen ions has a K reverse that is extremely large also. Therefore, the acetate ion can completely consume or snarf up hydronium ions. And so that is this equation where I have the acetate ion and hydronium ions can be completely consumed because the K reverse is so large. Remember, when you reverse the equation, you take 1 over the K value, and that's 5.6 times 10 to the 4. Also a very large number. Okay? So the preparation of a buffer must include weak conjugate pairs. That is, the conjugate acid and the conjugate base of each other. Those are a difference between a single hydrogen. The specific choice of a conjugate pair set is chosen when the pKa of the weak acid is closest to the pH of the buffer desired. In other words, when the hydronium ion concentration is approximately equal to the Ka of the acid. Okay? Make sure you highlight that whole entire sentence. That's really important. Okay? To fine-tune the conjugate acid-base pair to the exact pH that's desired for that particular buffer, the ratio of the number of moles of conjugate acid to conjugate base is adjusted appropriately for that specific pH. Okay? All right, so the preparation of a buffer with a pH of 4.30 is desired. What conjugate base pair is best and how is the buffer prepared? So I've got 3 different conjugate base pairs here. Okay, so these are all weak acids or weak bases. So therefore, these can all be possibilities here. Not one of these is a strong acid or a strong base. So I can't immediately cross out any one of them. What I can look up in a table is the Ka values. So I got the Ka values for the hydrogen sulfate, sulfate ion concentrate, or sulfate conjugate pair. I got acetic acid and acetate conjugate pair, and hydrogen cyanide and cyanide ion conjugate pair. Okay, I can also, from the Ka values, take the negative log of each of these and get their pKa values. Now, I'm going to look at this, and I want a pH of 4.30. So I'm going to read that sentence highlighted in the yellow. The pKa of the weak acid is closest to the pH of the buffer desired. The buffer pH desired is 4.30. Which pKa corresponds to this is 4.74. That is the closest one that matches this. Okay, so from the pH of 4.30, I should be able to get the hydronium ion concentration using this equation that we've used before. Okay, and that is hydronium ion concentration is equal to 10 to the negative pH. So 10 to the negative 4.30 is equal to a hydronium ion concentration of 5.0 times 10 to the negative 5 molar. Okay, now look at that value right there and correspond that to the Ka values, because remember the hydronium ion concentration corresponds to the Ka value, and that would be right there. So you can either look at the pH and the pKa, or the hydronium ion concentration and the Ka as combinations. And of course, this will let me know which buffer pair I'm using, and I'm using the acetic acid acetate ion conjugate pairs for this best buffer at 4.30. Now I need to fine tune it. So I'm going to look at this here, and I want a pH of 4.30. I have a hydronium ion concentration that needs to be 5.0 times 10 to the negative 5. So look at those values right there. We're going to be using those here in a moment. Okay. Now that the acetic acid acetate ion weak acid conjugate pairs are chosen, it's time to fine tune this conjugate pairs to acquire the exact pH of this conjugate pair. So we're going to write the equation here, okay, and that's the acetic acid plus water and its conjugate pairs of the acetate ion and the hydronium ion. Okay, we're going to write the Ka expression from this above information. That's products over reactants with the stoichiometric coefficients as exponents. Solids and liquids are not included. So I've got a Ka is equal to acetate ion times hydronium ion in the numerator. In the denominator is the acetic acid. Okay, this is equal to 1.8 times 10 to the negative 5. That's the Ka value that was given to me from a tabled value. Okay, we're going to rearrange this and solve for the hydronium ion. Okay, so the hydronium ion is equal to 1.8 times 10 to the negative 5 times the acetic acid in the numerator and the acetate ion in the denominator. Okay, look at that very carefully. Okay, now what we're going to do is we're going to remember that the hydronium ion concentration that is needed for that pH of 4.30 is 5.0 times 10 to the negative 5 molar. We solved for that already. We're going to substitute this value in to that equation that we had before. So hydronium ion is equal to 1.8 times 10 to the negative 5 times the acetic acid divided by the acetate ion. That's what we had. We're going to substitute in this hydronium ion concentration in for the hydronium ion. And we get 5.0 times 10 to the negative 5 on the left-hand side is equal to the Ka, which is the 1.8 times 10 to the negative 5 times the acetic acid divided by the acetate ion. We're going to finally solve for the acetate or the acetic acid acetate ion ratio. Okay, so that is here, right here, and that is acetic acid over acetate ion is equal to 2.78 divided by 1. Okay, so that is this critical fine-tuning that we need. So what does this mean? To make a buffer with a pH of 4.30, it takes 2.78 moles of acetic acid and 1 mole of sodium acetate. Remember, it's a salt, and the sodium does not contribute to the pH. We're going to mix this, and this will yield a buffer at a pH of 4.30, which was what was desired. It's really the ratio of the number of moles that is the most important concept in this problem. You need to get the ratio of the number of moles correct in order to get that pH value exact. Okay? It would be easiest to prepare a buffer, that is, to use equal volumes of 2.78 molar acetic acid and 1 molar sodium acetate solution to obtain a buffer with a pH of 4.30. That would be the easiest method. Okay? And once you mix them up, bam, you got a pH of 4.30. I used to do this all the time in my lab, or in a lab that I worked in, rather. Okay, here's a little bit of acid-base humor to tie this up here. Why do chemistry teachers like to teach about sodium hydroxide? Well, it's very basic stuff. Why do chemistry professors like to teach about ammonia? Because it's slightly basic stuff. Think about that. Okay, I am the Crazy Hat Chemist, and of course you can't have a video without a crazy hat. Got to figure out who I am wearing this hat. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. We're going to do another buffer calculation here in just a second here, so wait for the next video. I'm going to see you next time. Bye for now.